Swayam Prabha. Digital India. Educated India.
Welcome back to the video course on fluid mechanics. In the last lecture, we were discussing about the Navier-Stocks equations and its exact solutions. So, we have seen various cases wherever exact solutions are possible, but as we can see only few cases wherever a lot of simplifications are possible. The problem is so simple, domain is so simple, and a number of assumptions like say parallel flow, like that we can put forward, then only we can get an exact solutions. So, but most of the field problems wherever we try to solve real field problems, then you can see that these kinds of assumptions if we put, then the problem becomes so simplified and then we will not get the results what we expect. So, generally these kinds of the analytical solutions, just whatever the analytical solutions we discussed, say most of the field problems we cannot directly apply. So, we have to solve the Navier-Stocks equation with the continuity equations in its full form, and then we have to get the various parameters like velocity, pressure, vorticity or other kinds of parameters. So, to do this, so we do not have any shortcut, we have to solve the Navier-Stocks equation, say approximate methods or numerical methods. So, with the advent of the various computer technologies and advancement in say various numerical methodologies, now we are able to solve this Navier-Stocks equations and then try to get solutions for various field problems. So, here today we will discuss the various numerical solutions for the Navier-Stocks equations, and then we will discuss the various methodologies, numerical methods used briefly, and then say we will see how the applications of Navier-Stocks equation with respect to the numerical methods. So, the Navier-Stocks equation, the numerical solutions. So, here only few analytical solutions are available and approximate solutions, we have to go for approximate solutions. So, as I mentioned, high speed digital computers have helped a lot in this kinds of developments of called computational fluid dynamics. So, here what we are generally doing is the partial differential equations, which say the Navier-Stocks equation which we are seeing in 3 dimensions or 2 dimensions are partial differential equations. So, what we are trying through by using the numerical methods, we are trying to replace these partial differential equations by a set of algebraic equations. So, once this transformation is done, then we can apply the boundary conditions into the system of equations and then we can get the numerical solutions. So, as we are trying to solve the complete Navier-Stocks equation this way, by that means by using the numerical methods, then these numerical solutions we can apply for the most of the field problems. So, here The computation method, solution by approximate method. So, we are providing an approximate method, it may not be 100% right. So, various numerical methods are used. Say for example, when we consider the flow past a cylinder like this, you can see that we cannot approximate this kinds of problem. We have to solve the real Navier-Stocks equation, and then we have to obtain the various parameters like velocity, and then we can represent it visually like this, animate it, or we can represent in terms of graphical or other tabular forms. So, a wider class of mathematical formulations are possible. So, we have already seen the Navier-Stocks equation, 3 different forms like primitive variables. Then we have seen the velocity vorticity formulation and vorticity stream function formulation. So, depending upon the kinds of the problem, depending upon the type of the problem which we are trying to solve, we can formulate the problem mathematically, and then we can solve using the numerical solution. So, this branch of fluid mechanics called computational fluid dynamics, the Navier-Stocks equation are solved using the numerical methods, and then we try to solve the real field problem. So, now say commonly in literature a number of numerical methods are available, but generally you can see that we use 4 numerical methods like finite difference method, finite volume method, finite element method, and boundary element method. So, these are the commonly used numerical methods, same called finite element method, finite difference method, finite volume method, and boundary element method. So, each method has its own advantage and its own say disadvantages like various difficulties. So, the method say depending upon the problem, depending upon what kind of problem we are trying to solve, we can use any of this finite difference method or finite element method or finite volume method or boundary element method, and then we can try to approximate the Navier-Stocks equation and then try to solve. So, the selection of the methodology depends upon the say type of problem which we have to solve, and then say the familiarity of the user say using this methodology, and then the availability of the kind of computers which is required for the say typical like boundary element method. We have to solve a large system of equations. So, that kinds of methodology may need a slightly advanced computer. So, like that. So, depending upon the user and depending upon the problem, we can choose any of these methodologies. So, say for example, if you want to simulate what happens, say here you can see that we want to see this is a cube, we want to see the flow behavior or flow surrounding a cube. So, what we are trying to do is we will choose one of this methodology, and then we can discretize this domain. Say for example, here this is the domain. So, we can discretize the domain, and then we can say approximate the Navier-Stocks equations, and then as we have already seen, the partial differential equations will be transformed into algebraic set of equations, and then we will be applying the boundary conditions. Say for example, the boundary condition can be say in this figure what is entering from here. Say if we know the velocity at this location, and here we will be having a no slip condition, and then here what are the conditions. So, based upon the boundary conditions, we will be solving the problem. So, now say we will be briefly discussing all these numerical methods like finite difference method, finite volume method, finite element method, boundary element method very briefly, since only I want to discuss here is only say what is the methodology and which way we are trying to solve the problem. So, but otherwise each of the methodology say to describe or to explain to all the level, it will be very difficult. So, here we will be discussing briefly. So, first one is the finite difference method. So, in finite difference methods, the continuous variation of the function, so represented by a set of values at points on a grid of intersecting lines. So, what we are doing in a finite difference method, say let us consider say the flow in a square cavity like this, as we have seen this is a typical problem in 2D. So, what we are say in finite difference what we do, if this is the boundary is here gamma 1, gamma 2, gamma 3, gamma 4 and domain, this is the domain. So, what we will do in finite difference method is we will be representing this domain with respect to a grid points. So, here we can say just discretize the domain to grids, square or rectangular grids like this, and then say we will be representing the domain with respect to grid points. So, these are all the grid points here, and then say, so if this is x direction, this is y direction. So, we can represent each grid point, and then what we are doing the continuous variation of the function. So, the function can be the velocity or whatever the function we are trying to approximate. We will be representing the functions by a set of values at points on a grid of intersecting lines. So, you can see that a grid of intersecting lines here, and then the gradient of the function, say here if phi is the function which we try to approximate here, then we will be having the gradient like del phi by del x or del phi by del y. So, the gradient of the function is represented by the difference between, say, the differences in the values at neighboring points. So, you can see that, say, between this point and this point we will be trying to represent between the neighboring points. So, that is the way we represent in the finite difference method. So, between these 2 points we take, or between these 2 points to represent the del phi by del y. So, like this we represent the gradient of function represented by difference in the values at neighboring points, and we form finally a finite difference equation is formed. So, finally, after representing, say after writing the equations, say each grid point we can write the equations, and finally we are representing the partial differential equation. Say in this case the Navier-Stocks equation and the continuity equation will be representing in terms of difference equation. So, we form the difference equation, and at the grid points this equation is used to form a set of simultaneous equations. So, we have various grid points as explained here. So, this equation is used to form a set of simultaneous equation, and finally, it gives a value of the function at a point in terms of the values at nearby points. So, once a set of we form the difference equations, and then we will be knowing the boundary conditions, or at least a few grid points we will be knowing the values. So, with respect to the known values, we will be trying to find out the unknown values between the unknown values at a point in terms of the values at the nearby point. So, this is the procedure used in finite difference method. So, we obtain the value of the function at a point in terms of value at nearby points. So, if there is any specific case at the edges of the grid, value of the function is fixed, or a special form of finite difference equation can be used to get gradient of the function. So, depending upon the problem, say at some places we have to say what we discussed here is only the basic of the fundamental which way the finite difference method is working. So, there is a lot of number of variants of finite difference are available in literature. Then also the variation with respect to space, with respect to time, there are number of methodologies for the finite difference method available. So, they essentially what we are doing here is, as we have already discussed, between 2 grid points we see the difference, say the gradient, and then we try to approximate the governing equation, say here Navier-Stocks equation, and then write that difference equation, and then solve the difference equation with respect to the known values or the boundary conditions. So, this is the finite difference method. Then another important methodology used in computational fluid dynamics is the finite volume method. So, here say finite volume method, you can see that a large number of CFD codes are nowadays written using finite volume method, since it has got a number of advantages. So, these finite volume methods are particularly applicable to irregular and unstructured grids. So, we have seen that finite difference method generally say we use a square or rectangle type grid. So, wherever irregular shape comes or unstructured grids, it will be more difficult to deal. So, finite volume method has advantages over finite difference method to deal with the irregular or unstructured grid. So, if you consider the finite volume method for a generic conservation equation like this, say del of rho uj phi by del xj, del by is equal to del by del xj gamma del phi by del xj plus q phi. So here phi is the function, u is the velocity vector, rho is the density, and q is the source sourcing. So let us consider typical equation like this. So by using the finite volume method, so here we consider the individual cells like this, and so it can be regular cell structure like this, rectangle or square, or we can have any shape of the cell. And then the finite volume method, the domain is discretized, and then as a set of nodes and grid cells. So you can see that the nodes can be on the intersection or it can be at the middle. So here we will assume the grid nodes are located at the grid cell centers. So this is not the only option, other way also it is possible. So then compared to the finite difference method, the starting point for finite volume method is an integral form of the conservation equation. So the conservation equation which can be, we will write in the integral form like this: integral with respect to the say with respect to s, rho phi v dot n ds is equal to integral s gamma gradient phi dot n ds plus integral omega q phi d omega. So we write the equation like this, which we have already considered. So we are integrating with respect to the cell which we consider. So here we will assume that the density, velocity component, sourcing terms are known, and the unknown is phi. So then we can obtain the solution. The net flux through the phases of the control volume via convection and via diffusion. If it is required, we can write integral s f ds is sigma k integral s k f ds. So we can integrate throughout the various cells. So we can obtain the surface integrals are calculated in terms of nodal values of f. So this is a brief procedure as far as finite volume method is concerned. So here, compared to the finite difference method, as we have discussed earlier, say if we consider the Navier-Stocks equations, and then any kind of irregular domain, we can use the finite volume method. And then so here basically we discretize the domain into cells, and then we consider the grid point either at the center or at the intersection of the grid, and then we approximate the equation as we have already discussed, and then we integrate with respect to the cell to get a solution. So this is the briefly, very briefly, if you say finite volume method works like this. So we can approximate Navier-Stocks equation using the finite volume method, and then we can try to solve for various problems. So this is the finite volume method. And then another important methodology used is called finite element method. So here the region of interest is divided in a much more flexible way, and the nodes at which value of the function is found have to lie on a flexible mesh. The boundary conditions are handled in a more convenient manner. There are number of approaches in finite element method. So some of the commonly used methodologies are direct approach, variational principle, or a weighted residual method to approximate the governing differential equation. So for example, if you consider the problem which we considered earlier, like the square cavity problem. So using the Navier-Stocks equation, if you want to solve, say let us consider a cavity like this, and then if u is equal to 1, here v is equal to 0, so here uv is equal to 0, uv equal to 0, uv equal to 0. So if this is the problem, then what we do here, this compared to the finite difference method, this is much more flexible in finite element method. So what we can do, we can discretize the domain. Say let us, instead of rectangles or squares, we can use triangle elements like this also. And so the advantage here is it is much more, methodology is much more flexible compared to the finite difference. Different kinds of elements, like say we can have triangles, or we can have rectangle or square, or we can have say quadrilateral like this. So here this is called an element, and say we define here the nodes. So these are called nodes, and here various shapes of elements are possible. So the advantage here compared to any other numerical method, so here we can have different shapes of elements, and so we can easily deal with any kind of irregular domain, and then say we can fit the domain with an exact very accurate mesh compared to the grids which we used in final difference method. And then say after the meshing is over, then we will be say defining an interpolation function, the variation like the velocity or the parameters which we consider, say in Navier-Stocks equation either the velocity or pressure, then we will be approximating these functions of or the parameters, velocities and pressure with respect to an interpolation function, and then we will be trying to approximate the function with respect to the interpolation function, and then we will be putting back to the say the given equation, and then we will try to say orthogonalize it. Say for example, one of the methodology, the Gagliarkin finite method, we try to orthogonalize with respect to the interpolation function or the shape function, and then we force the error to 0. So, since say we are approximating with respect to the interpolation function, solution will not be exact. So, we are trying to force the error, the residue produced to 0, so that the error is vanished, and then we will get an approximate solution. So, as discussed in finite element method, there are a number of methodologies like direct approach. Say for example, when we try to solve say a network of pipes, there we can directly use the Darcy-Weisbach equation to get a relation between various pipe elements. So, that kind of problem we can solve using the direct approach, and then another important methodology is called variational principle. So, variational principle generally say we have to derive a function, variational function for the given equation which we consider, and then we are trying to approximate. So, this variational principle generally we use for structural mechanics problem. And then another important methodology is the weighted residual method. So, there say we are approximating with respect to the interpolation function, and then we are trying to, while approximating a residue will be say due to error, the residue will be made, and that residue will be forced to 0. So, that is what we generally use, the method of weighted residual approach. Say one of the commonly used methodologies, Gagliarkin approach. So, like this different methodologies are there in finite element method. So, say for example, here if you consider say the say in this domain there is a cylinder, and if you want to see that how the movement of a sphere inside the cylinder. So, what we can do is we can discretize using say in 3 dimensions, we can discretize the domain like this, and then we can solve the Navier-Stocks equation 3 dimensional. So, that say we can initially transform the partial differential equation Navier-Stocks equation into algebraic set of equations, and then we can apply the boundary conditions, and we can solve those system of equation to get the unknowns. So, this is the essential principle behind the finite element method. So, this finite element method is also very much say lot due to its advantages, number of advantages are there compared to the finite difference method. So, finite element method is also very commonly used to solve various fluid flow problems by using the Navier-Stocks equations. And then lastly, another say methodology recently developed, recently means about say in the 1970s, it was the methodology, the development of this methodology has been started. It is called a boundary element method. So, here in boundary element method, the partial differential equations. So, here the partial differential equation means the Navier-Stocks equations describing the domain is transformed into an integral equation relating only to the boundary values. So, here the boundary element method is based on the Green's integral theorem. So, if you go to the advanced mathematical textbooks, we can see that Green's theorem like Green's first theorem, Green's second identity theorems are there. So, here the Green's theorems are used to transform the equation which is on the domain to the boundary. So, here we discretize the boundary instead of the domain, and then if you want to find out the parameters on the once we can discretize the domain and say solve for the, you will get the equation in terms of the boundary integral, and then we can say for example, we can find out the unknowns initially on the boundary, and then we can find out the unknowns on the on the domain. So, here say for example, in boundary element method, if this is the domain which we are dealing, so we will be discretizing like this using various nodes and elements, and then if you want to find out the, so this is called a node and this is called a element. So, once we find, say for this particular problem, say if the, say the velocity here is known and some other portions the velocities are not known, then we can find out first on the boundary, and then various internal points we can define separately after the boundary integral equations are written, and then we can solve for the unknowns on the inside the domain. So, this is internal nodes. So, the advantage here is, so since we are trying to solve initially on the boundary, so the computational dimensions of the problem will be reduced by 1. So, due to this, a 3-dimensional problem we can solve in 2 dimensions, and a 2-dimensional problem computationally we can solve in 1 dimension. So, that this is one of the advantage of this methodology, but it has got its own limitation also, since here to solve the partial differential equation, then we have to look for a fundamental solution in the boundary element method. So, to derive a fundamental solution, it is very difficult for the complicated equations like Navier-Stocks equations, but now recently there are some other methodologies like dual reciprocity boundary element method has been developed. So, we can still approximate the given equation with respect to some other methodologies like dual reciprocity method. So, this is the essential of the boundary element method. So, here say as I mentioned, say if you want to solve a flow through a dam, then we will be discretizing like this, then you can see the elements 1, 2, 3 like that, the elements and nodes we will put, and then we will try to solve. So, as far as fluid flow problems are concerned, it is ideally BEM is ideally suited to the solution of many 2 and 3 dimensional problems, especially potential flow problems. To solve the full Navier-Stocks equation, this methodology has got some limitations, but the advanced techniques like dual reciprocity method can be used, but otherwise the methodology BEM is much more used to solve potential flow problem. So, in comparison, so while using finite difference method, finite volume or finite element method or boundary element method, we generally model say like say for example, if you consider the flow through dam like this, then this finite difference discretization is shown here, finite corresponding finite element discretization is shown here, and boundary element discretization is shown here. So, as I mentioned, so depending upon the problem, depending upon the familiarity of the user with the methodology, then we can choose the methodology and then we can try to solve. So, in using in say any of this numerical method, so there are essentially 3 steps. First one is the pre-processing. So, here pre-processing means first we will be discretizing the domain by putting the grids or mesh like this, and then we will be putting the boundary conditions and then various parameters which are generally available before say for the problem considered. And then processing means second step is the processing. Processing means the computer code which we will be writing for the methodology, then we have to run the code to generate the solution for the particular problem, and then third step is the post processing. So, post processing means once the results are generated, we will be getting numbers, that numbers we have to put it in the graphical forms or the tabular form, so that the other people can understand which way the solution has been generated and how the results are. So, essentially we have 3 steps. One is pre-processing, second one is processing, and third one is post-processing. So, that is about the numerical methods to solve the Navier-Stocks equation for say various problems by using different methodologies. So, before closing this chapter, we will be discussing 2 more say a typical problem where analytical solutions or where we can approximate the Navier-Stocks equation and then trying to get analytical solution. First one is the creeping flows. So, actually the second one also which we are discussing is the groundwater flow, that is also we can classify as a creeping flow, as a subsection of this creeping flow. So, here creeping flow means it is the flow is extremely slow motion of the fluid in a prescribed geometry. So, here generally the Reynolds number will be very low. So, it will be generally less than 1, and so here you can see this is the flow in a domain, say the lava flow from a volcano. So, you can see that the viscosity is so high, and then the motion will be so slow, and then you can see that we can classify these kinds of flow as creeping flow. So, here the spatial acceleration terms in Navier-Stocks equation we can neglect, since the Reynolds number is very low, less than 1. So, if you neglect the spatial acceleration terms, and then we get a simplified form of the Navier-Stocks equation. So, generally we can represent for creeping flows, we can represent the equation as del P is equal to mu del square U, where P is the pressure, mu is the coefficient of dynamic viscosity, U is the velocity. So, here when the inertial forces are neglected, generally the solutions are valued for approximately for Reynolds number less than 1, and the Navier-Stocks equation reduced to this form, and then this form of the Navier-Stocks equation and the continuity equation we will be using for the solution of these kinds of creeping flow problems. So, as we have discussed, the flow is in slow motion due to the high viscosity, or depending upon various other conditions or situation, the flow is in the velocity is very low, slow motion. And here if we use the stream function instead of terms of head or the velocity, equations will be simpler if stream function psi is introduced. So, we can represent u is equal to del psi by del y and v is equal to del psi by del x like this, and then we can rewrite the governing equations starting from the Navier-Stocks equation, and then after rewriting we can say trying to solve the problems of the like what we discussed in the case of creeping flows. So, a number of problems can be solved in this category of creeping flows. So, variety of practical problems like motion of particulate matter in liquids and gases, say just like say when say if you consider reservoir, the sediments will be settling since the water is stored. So, the settlement of sediments we can consider as a very slow motion, and then try to get a solution for this kinds of problem. Or the dust particles, the settlement of dust particles in the atmosphere, or the mist, the simulation of mist in the atmosphere, or say like bubbles and drops in chemical reactors, or flow of molten metals. All these problems comes under the category of the creeping flows. So, also as I mentioned, this groundwater flow and lubrication problems also we can classify as a section of the creeping flow. We can approximate as a creeping flow. So, these are some of the applications of the creeping flows. So, here we will consider two cases. One is the Stokes flow and the second one is the groundwater flow. So, first case is Stokes flow. So, here say by using this creep flow theory, Stokes tried to solve by starting from the Navier-Stocks equation. He approximated the Navier-Stocks equation in the simplified form, and then he got a solution by end of the 19th century itself. So, here Stokes flow deals with the uniform motion of a sphere through a large expanse of viscous fluid at small Reynolds number. So, Stokes flow deals with say as I mentioned, this can be used in the case of sediment settlement in reservoir, or while dealing with the dust particle in atmosphere we can use this theory, Stokes flow theory. So, this solution has been derived by Stokes by end of the 19th century, and the flow is at low Reynolds number. So, here you can see we consider the as a single particle as a sphere here, and then this shows the streamlines and velocity vectors are also indicated. So, Stokes considered the motion of a sphere through a large expanse of viscous fluid at small Reynolds number. So, while deriving the solution, he put forward a number of assumptions so that the problem will be simpler, and then he got a solution for the problem. So, here the assumptions used are the inertia forces on the fluid particles are small and may be neglected in comparison to the viscous force. Then second assumption is walls of the vessel containing the fluid element is not here. So, it is so that the effect of the walls are not there when we deal with when he derived the equations. And then also some other assumption like no slip between the fluid and the boundary of the space, and then he also assumed that the sphere which we considered is rigid, and to derive a solution he used only a single sphere. So, these are some of the assumptions used by Stokes to derive this solution called a Stokes solution. So, here if we consider the force resisting the motion of the sphere, that is the drag on the sphere, Stokes obtained the drag force F d is equal to 3 pi mu into V into d. Here we should note that Reynolds number what Stokes assumed is less than 0.1. So, where V is the velocity of the sphere relative to the undisturbed fluid, and mu is the dynamic viscosity of the fluid, and d is the diameter of the sphere. So, Stokes derived the drag force is equal to 3 pi mu into V into d. So, for the fall of relatively small bodies through the fluids of relatively high viscosity like the dust particle, mist droplets in the atmosphere, and the settlement of silt in reservoir, etc. Same we can consider, say for example, if you consider for a small solid particle falling through the fluid, it will accelerate until the net downward force on it is 0. So, if you consider, say as I mentioned, either dust particle or the sediment particle in the reservoir, so it will be keep on falling until the net downward force on it is 0, and then we can use this the drag force derived by the Stokes, and when the submerged weight of the particle is equal to the drag force F d, it will reach to the steady state of its motion. So, Stokes wrote the equation like this: submerged weight is equal to resisting force. So, here if we consider a single sphere of diameter d, we can write pi d q by 6 into gamma s minus gamma is equal to 3 pi mu V into t, where gamma s is the specific weight of the solid and gamma is the specific weight of the fluid. So, from which we can get the terminal velocity, that means when the submerged weight of the particle is equal to the drag force, it will reach a steady state of its motion, that velocity is the terminal velocity. So, Stokes got the terminal velocity as V is equal to d square by 18 mu into gamma s minus gamma. So, this solution is called a Stokes solution or Stokes law. So, this has got application in number of fields as I mentioned, like say reservoir sedimentation or say dust particle analysis in atmosphere. Number of applications we can use this Stokes law. So, this has been derived by Stokes in 19th century. So, he approximated, here also we can see that he approximated the Navier-Stocks equation and simplified the equations such that the very low Reynolds number problem we can apply as derived by the Stokes. So, finally, an expression for drag can be written as drag d is equal to C d into pi r square into 1 by 2 rho v square, where r is the radius of the sphere which we consider. So, coefficient of drag from this expression, coefficient of drag has been derived by Stokes as C d is equal to 24 by R e, where R is the Reynolds number, with Reynolds number R is equal to V d by nu, where V is the velocity, d is the diameter, nu is the kinematic coefficient of viscosity, and d is the diameter of the sphere. So, like this we can get the coefficient of drag, and then later Osin tried to solve this, again approximated. He obtained an improvement of Stokes solution by considering some of the initial terms in the Navier-Stocks equation, and he got the coefficient of drag as 24 by R e into 1 plus 3 by 16 R e, where R e is the Reynolds number. So, Osin tried to improve the Stokes law or Stokes equations. So, here as we have seen, this problem has got number of application. But it is a simplified form of the Navier-Stocks equation, and then Stokes derived the equations. So, depending upon the problem we can say for the particular case which we consider, we can use this Stokes law whenever the Reynolds number is very low, and then the say to determine the terminal velocity for the fluid particle which we consider. So, the second problem which we want to discuss here is the flow through porous medium. The porous medium consists of pores between some particular phase in the control volume. So, this is another important section of the fluid mechanics called groundwater flow and contaminant transport problem. So, here say if you consider, say if you have got a domain like this, and then if there are number of particles like this, then we can consider the Navier-Stocks equation for this kinds of flow problem, and then here also you can see that the velocity will be so low, so that we can approximate the say the flow is coming like this and going through this, and then you can see that due to the flow is taking through the pores only, and then on the particles like a sand particle, then the velocity will be much lower through the interstices of the pores, so or of the medium. So, here we can use the Navier-Stocks equation and approximate as creeping flow, and then we can use the equation. So, here we can approximate it, and so generally say the basic equation for porous media flow is the Darcy's law. So, here what we are trying to do is say whatever the theory for the laminar flow through pipe, we can try to apply for these kinds of problems. So, you can see that whenever we consider a medium like this, here between the sand grains, you can see that there is say the flow is taking place like this. So, the flow will be going like this through the different pores. So, what we do here try to do is say we try to approximate this problem as a pipe flow, that means between the solids we consider same pipe flow, and then we compare with the Darcy's, we try to obtain the Darcy's law from this theory. So, Darcy has done this experiment through the porous media, and he has derived and he has shown that the velocity of flow is proportional to the hydraulic gradient. So, here the Darcy's law is the basis for the study of this porous media flow. So, it has got a number of applications like groundwater flow of gases and polymers through porous structures, etc. Number of applications are there. So, here first we are trying to correlate with respect to the laminar equations which we derived for pipe with respect to this typical porous media flow. So, the Darcy's law, as I mentioned, it states that velocity of flow through the porous media is directly proportional to the hydraulic gradient of the media. So, mathematically we can write V is proportional to I, or where I is the hydraulic gradient, or we can write V is equal to K into I, where K is known as coefficient of permeability. K is called coefficient of permeability. So, here if you consider the porous media which we are discussing as a simple case of pipe flow equation which we have derived for laminar case. So, we have already seen earlier P1 minus P2 is equal to 32 mu UL by d square. So, where mu is the coefficient of dynamic viscosity, u is the average velocity through the pipe, L is the length of the pipe, d is the diameter, and P1 is the pressure at section 1 and P2 is the pressure at section 2. So, this we can write as this is P1 minus P2 is equal to K into mu into UL by d square. So, if we assume what is happening is between the solid grains or the sand grains, if you consider the flow taking place, the porous media flow as similarly as a pipe flow. So, we can consider the relation of flow through porous media with a characteristic length as grain diameter of the porous media. So, here we consider this L, the characteristic length, as the grain diameter of the porous media. So, considering the porous material in a tube of area A, and let the flow takes place under the piezometer head difference, HF is equal to H1 minus H2, and the velocity U is equal to average velocity U is equal to flow Q divided by area A. So, then we can put in this relationship as the actual flow area. So here we are trying to what we are trying to use is we are trying to correlate with respect to the pipe flow equation and the porous media flow. So but the porous media flow is concerned, you can see that since here you can see there is number of pores, and then say sand grains are there between the pores only the flow is taking place. So actual area will be reduced. So we can write the actual area, actual flow area, we can write as A into if A is the cross sectional area, so A into E, where E is the porosity of the media, E is the porosity which is the ratio volume of pores to the total volume. So E is defined as the porosity of the media. So the actual area is A into E. So that we can write, hence actual mean velocity is equal to Q by A into Q by A E. So that is equal to Q by A is U, so U by E. So the whatever we consider the mean velocity is U, so that has been, we have to divide it by E, the porosity, so that actual mean velocity is equal to U by E. So now we can rewrite the equation which we have written here as P1 minus P2 is equal to K into mu into U into L by E into ds square. So here ds is defined as the grain diameter of the porous media. So or we can write this, we can divide by gamma and write as HF is equal to, HF is P1 by minus P2 by gamma. So HF is equal to K mu UL by gamma E d ds square. So finally from this expression we can write the velocity U is equal to HF by L, which is the head loss, HF is the head loss, HF by L into gamma into E into ds square by K into mu, or from this we can write as this HF by L is the hydraulic gradient, that means the head loss with respect to head loss, U is equal to HF by L into gamma into E into ds square by K mu, or we can write U is equal to K dash into I, where I is the hydraulic gradient, I is HF by L. So this expression U is equal to K dash I is known as Darcy's law. So here K dash is equal to gamma into ds square by K into mu as per this expression. So this is called the coefficient of permeability. So here what we did is, so we tried to approximate, so we tried to use the equation which we derived for the pipe flow, and then between the sand grains we tried to get the actual velocity, and then we obtained the velocity, and then that is the Darcy's law, that is what proved by Darcy through experiment. So you can see that this Darcy's law is applicable up to a Reynolds number generally equal to 1, where Reynolds number is here is defined as U ds by nu, where ds is the grain diameter and nu is the kinematic coefficient of viscosity. So as we have seen here, so this groundwater flow is also as an approximation of the creeping flow theory which we have seen. So the Gaviani equations, so here also the Gaviani equations, we can start from the Navier-Stocks equation and then put forward the various assumptions, and then we can simplify the equation, and then we can try to get solutions. So through the simplification of the Navier-Stocks equation, say for example, first if you consider steady state porous media flow in the homogeneous isotropic porous media, the Gaviani equation is Laplace equation, we can write from the Navier-Stocks equation, we can derive this form of the equation, del square H is equal to 0, which is the Laplace equation, where H is the head of the or the water table height for the problem considered. So like this we can also start from the Navier-Stocks equation and then try to get solution. So as I mentioned, this porous media flow is also very complex type of flow problem. So this also here also we can use the Navier-Stocks equation. So as this slide shows, say for example here this slide shows the flow through the fiber web structure which can be considered as the porous media flow. So here the velocity field is also marked, and then you can see that here also path lines are also marked. So these kinds of, so the porous media flow as we can see here is so complex, but still we can use the Navier-Stocks equation and then approximate, and we can try to get for simplified cases like flow through steady state flow through homogeneous isotropic media. So we can try to get solutions. So this flow through porous media also has got number of applications, like we have already seen in the aquifer studies, then contaminant transport studies, and filter design, gas coolant system design, geological flow simulations, groundwater remediation studies, oil exploration studies, etc. A number of applications are there for porous media flow. So, this is actually say related to the groundwater flow, where course on groundwater flow can be discussed in detail, but here as a part of, so the aim of this discussion is we start from the Navier-Stocks equation also, we can get the simplified equation for the porous media flow, and then for simple cases like say the steady state flow through homogeneous isotropic media, we can try to get solution. So, like this various kinds of flow problems can be attempted, can be solved using the Navier-Stocks equation. So, to summarize this chapter, so here the Navier-Stocks equations, so derivation and exact solutions and solution, numerical solutions we have seen. So, to summarize, so viscous flow, most of the flow problems which we consider in practical cases or real life is viscous flows. So, we have to consider the viscosity in nature, it can be Newtonian or non-Newtonian depending upon the problem. So, for Newtonian problems, this viscous flow problems, we have derived the Navier-Stocks equations. So, this Navier-Stocks equation is a general form of the viscous fluid flow equations. We can solve most of the problems with respect to the Navier-Stocks equations, including the turbulent flow problems or even the compressible fluid flow, by appropriately modifying the governing equations. So, these equations are applicable to most of the fluid flow problem, but due to the nonlinear and second order nature of the equations, only few analytical solutions, only for simplified problems analytical solutions are available, but most of the real field or real life problems we cannot use the analytical solutions. So, to use the Navier-Stocks equation, we have to go for numerical methods and numerical solutions as we discussed. So, these numerical methods or numerical solutions of the Navier-Stocks equations, which we generally call as computational fluid dynamics CFD, we can solve most of the problems by using the Navier-Stocks equations. So, this is the end of this Navier-Stocks equation chapter. So, the next section we will be discussing about the boundary layer flow and its governing equations and various solutions.